Now, let's try to see what will happen if we're considering two IO-bound tasks. And again, we'll think of two tasks that have execution time of 10 seconds and in a system that has a context switch overhead of 0.1 second. And let's also assume that the nature in which these IO calls are performed is that a task issues an IO operation every 1 second. And let's also assume that every single one of those IO operations complete in exactly half a second. If we look at the timeline, it looks identical as what we saw in the case for the CPU-bound jobs with a time slice of 1 second. This makes sense because exactly after 1 second, the tasks are, in this case, not exactly preempted. They actually end up issuing an IO operation, so yielding voluntarily regardless of the fact that the time slice is 1. So if we look at the performance metric for this case, they will be identical to the previous case in the case of the CPU-bound tasks. Now, if we look at the second case that has a time slice value of 5 seconds, we see that the timelines, the schedules of the two tasks, are identical to the case when we had a much smaller time slice value of 1 second. Similarly, obviously, if we compute the metrics, they will be identical. It's for two identical schedules. The reason for this is that at this particular moment, we're not exactly time slicing. We're not interrupting the tasks in either one of these cases. The IO operation, again, is issued every 1 second. So regardless of the fact that in this scenario, the time slice value is much longer, we still end up issuing an IO operation at the end of the first second. And therefore, the CPU is at this point released from T1. T1 yields, and T2 is free to be scheduled and to start executing. So one conclusion that you can make from this is that for IO-bound tasks, the value of the time slice is not really relevant. Well, let's not draw that conclusion that fast. Let's look first at a scenario where only T2 is an IO-bound task. T1 is a CPU-bound task, as what we saw in the previous morsel. In that case, the execution for the two tasks T1 and T2 when the time slice is 1 will look the same. The one difference is that in the event of T1, we preempted after 1 second, whereas in the case of T2, the IO-bound task, after 1 second, it voluntarily yields since it has to go and wait for an IO operation. In the case of 5 seconds, the execution of T1 and T2 will look something as follows. T1 will run for 5 seconds, and at that point, its time slice will expire, so it will be preempted. T2 will be scheduled, and as an IO-bound task, T2 will yield after 1 second because of waiting on an IO operation. At that point, T1 will be scheduled again. Now, at this point, T1 is actually complete, so T2 is the only runnable task in the system, and that's why we have this illustrated in this manner. If we work out the performance metrics for this last case, the numbers will look as follows. And again, for all of these, the calculations are posted in the instructor notes. We see that both with respect to throughput and the average wait time, the use of a smaller time slice results in better performance. The only reason why in this case the average completion time is so low that if you look at the calculations, there is a huge variance between the completion time of T1, which is at 11, and then T2, which is way later. We see from this that for IO-bound tasks, using a smaller time slice is better. The IO-bound task with a smaller time slice has a chance to run more quickly, to issue an IO request, or to respond to a user. And with a smaller time slice, we're able to keep both the CPU as well as the IO devices busy, which makes obviously the system operator quite happy.